Okay. Well, so chemical thermodynamics, we're really concerned about this concept of equilibrium. Equilibrium is when no changes occur within the system, which, is pretty obvious. You might not need to write it, but no changes occur within the system. So equilibrium conditions are when no changes occur within the system. What are some types of equilibrium that you know about or that we've already looked at in this class? So specific types of equilibrium. Yeah, Hannah, thermal equilibrium. So we have thermal equilibrium, like question 3 on exam 2. Oh wait, I'm spelling equation, not equilibrium. Thermal equilibrium. Thermal equilibrium, and this is where we have no change in temperature. No delta T of our system. So we're at thermal equilibrium when we have no change in equilibrium in or no change in temperature in our system. We also have other types of equilibrium. Anybody know any other ones? Pressure equilibrium, yes, but we don't call it pressure equilibrium. We call that mechanical equilibrium. Mechanical equilibrium is when there's no change in pressure. So mechanical equilibrium is when there's no delta P. So this is something like a throttling system or a gravity-fed turbine where we have no occurring change in pressure. So the pressure is pretty constant. This can also be relevant to some gas systems, but essentially mechanical equilibrium is when we have no change in pressure in the system. We also have phase equilibrium. Phase equilibrium. So isobaric means there is no change in pressure. But isobaric means there's no change in pressure across the whole system. So it doesn't necessarily mean that we're at an equilibrium point. So isobaric can also be it's being held at a constant pressure. But typically thermal equilibrium is where something is heating up and cooling down and then it gets to equilibrium and there's no more change in pressure. There's no more change in temperature. Mechanical equilibrium, so you have a throttling valve, you're changing the pressure, eventually you're at equilibrium, there's no more change in pressure. So it's different than adiabatic or isobaric or isothermal, any of those. So phase, sorry, let me silence this. Phase equilibrium is when we have no change in phase. So this is relevant to saturated liquid vapors. We have this kind of, part of it's turning into a vapor over time. Maybe it's becoming superheated, maybe it's cooling off. But thermal equilibrium is where we have no more of this phase change. So that's at phase equilibrium. We're kind of staying at this one specific phase. And then lastly, and the one that we're focusing on for these chapters, chapter 15 and 16, is chemical equilibrium. Chemical equilibrium. And this is where we have no change in chemical composition. Composition. Who knows if that's right? Chemical comp. All right, so we have these different conditions of equilibrium, and then we also have something that kind of plays hand in hand with equilibrium, but in a more general sense. So the second law of thermodynamics. Does anyone remember the second law of thermodynamics? Yep. So the second law of thermodynamics is saying that entropy is always increasing. We are going from ordered systems to less ordered systems, quality energy to lower quality energy. Heat is always dissipating in the world. We are always we are always going to more chaos, lower quality, and less organized. So it's true about like your household, it's true about your appliances, it's true about chemistry, it's true about everything, right? So the second law of thermodynamics, um, yeah. Well, normally I do go to chapter 6, but I'm skipping over to chemical thermodynamics right now because I was told by the environmental chemistry instructors that it would be very helpful if we had more chemical thermodynamics taught in thermodynamics for the environmental chem sections that you teach next year. So I've expanded it, and I'm really going to be making sure that it's well ingrained by the time you get to environmental chem, and then that should make environmental chem a little bit easier and make it easier for both you and them. So that's kind of why I'm skipping chapter 6 for now and trying to expand chemical thermodynamics. Okay, so second law of thermodynamics, the entropy of the universe is always increasing for any spontaneous process. So there's several ways that we can phrase this. There's also the quality always flows towards less organized, heat is always dissipating. But for chemistry, we're really going to focus on the entropy of the universe is always increasing for any spontaneous process. The entropy of the universe is always increasing for any spontaneous process or any spontaneous process. The entropy of the universe is always increasing for any spontaneous process. So entropy being a measurement of like disorder and chaos, kind of. That's a very, very simplistic way of saying it, but we can also write this as the change in entropy being represented by an S. Change in entropy is always going to be greater than or equal to 0 for any spontaneous process. So one example will be if you have a glass of water with blue food coloring. So you have this little, you have a glass of water and you have this little container of blue food coloring that's really condensed. When you first drop it in, it's still kind of like organized in that drop pattern, and it's going to slowly dissipate out, and you're never going to be able to get all of that blue food dye back out without losing some water, losing some food dye, losing whatever. So you're always kind of going to this more dissipated form of energy, this more dissipated form of your chemistry, often losing some to heat or losing some of your organization over time. And even if you were to try to, boil the water and get the food coloring back out, which you can't really do because food coloring is also a water-based. So maybe if you were trying to filter it, blah, 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 you're never going to get it back to that original like condensed state and then basic water. So you're always going to have this process where you're getting more dissipated, more entropy, more heat loss over time. Okay. So for chemistry, when we're talking about this, we also need to consider the fact that chemical reactions can proceed both forward and backwards. So a reversible reaction can proceed both forward and backward. A reversible reaction can proceed both forward and backward. which I represent by this like forward arrow and backward arrow when I talk about chemistry. So for instance, A moles of a compound A plus B moles of a compound B can go in either direction, forward or backward, to form C moles of compound C plus D moles of compound D. These are just like generic compounds. Is this chemical equilibrium similar to that of fundies? Yes, it is similar to fundies, but we're going to focus more on the thermodynamics of chemical equilibrium than we did really in fundies. But yeah, it's the same. Chemical equilibrium is always going to be the same. Yeah. So this is generic formula. You could have more reactants, more products, less, whatever. This is just kind of a basic breakdown of reversible reaction. And at equilibrium, the rate forward equals the rate backwards. So for this equation, at equilibrium, the rate forward equals the rate backward. So you may still have some of compound C forming, but you have just as much of compound A or B forming too. That rate that's forming of the products is the same as the rate that's reforming the reactions at equilibrium. So the rate forward, this rate here, is going to be the same as the rate backward. So we're at this equilibrium point where the rate forward is the same as the rate backwards. It doesn't mean that these moles are equal. It doesn't mean that we're at the same temperature. It doesn't mean anything about pressure or quantity. It means that the rate of the forward reaction is the same as the rate of our backwards reaction. Okay, so all of you should also have seen this in fundies. I teach it slightly differently, but it's the same exact concept. So in order to evaluate the rate of this forward and backward reaction, we use our equilibrium quotient or constant. So equilibrium quotient or constant. And this value is that KEQ value. So EQ representing equilibrium, K being a generic constant term. So our equilibrium constant, our constant that is representing when we have the same rate forward as the rate backwards, is equal to our compound C raised to its molar, this is a capital C, raised to its molar concentration, our compound D raised to its molar concentration, over our compound A to its molar, and then B to its molar. So these being our reactants, our products. Over our reactants. So you should have all seen this in fundies. Hopefully you're like, oh yeah, I know this, blah, blah. But important considerations, solids and liquids have a value of 1. Let me make sure I'm phrasing that right. think I might just want to say solids here and not make it confusing. All right, I'm going to make this just solids here, and we'll do some examples. There are some, well, no, okay, I'm just going to leave it like this. Okay. Yeah, so yeah, I agree. So pure solids and pure liquids, liquids like water are going to have a value of 1. However, if you have chemicals that are dissolved in an aqueous solution, like technically your solution is a liquid, but your like the chemical that you're looking at is just in an aqueous solution. So those don't have a value of 1. And then gases, we're going to use partial pressure. So gases use partial pressure. Okay, I'm going to write this smaller so I have more room at the bottom. Gases, we use partial pressure. All right, and then so if we have a KEQ value that we consider to be large, so our KEQ is greater than about 1,000, are we going to be all products, all reactants, or some products, some reactants?
I think it would be like more products than reactants, but I don't know if you can have like all products and no reactants, if that makes sense.
Okay, yeah. And Layla says some. Other ideas? Okay, well, if we're gonna look at this ratio, like Emma did, if we have a very large KEQ value, that means we either have a very small number on the bottom or a very large number on the top. So either way, we have a very small amount of reactants or we have a very large amount of products. And so if we have a small amount of reactants, we're probably going to have a relatively larger amount of products. So you're right, this is going to be all products or relatively all product. If we have a small KEQ, by the same logic, so a KEQ that is less than 0.001, a very small KEQ, this is where we're going to have a much larger amount of reactants than we do products, hundreds of times, thousands of times larger ratio wise. So here we're going to have all reactants. And then if we are between 0.001 and 1,000, this is where we have some products, some reactants. And this is really where we're mostly going to be working problems. But it's important to always keep in mind that KEQ is a representation of this ratio of your products to your reactants. So the larger it is, the more your product favored reaction. So the higher the value of KEQ, the more product favored at equilibrium. Because remember, KEQ is only giving us information about equilibrium. It's also important to know for KEQ values and chemical equations in general, you must have temperature and pressure information. Must have temperature and pressure information. And if you are at standard temperature and pressure, a lot of times this is denoted by a superscript of not. So this is just a generic variable X, and then I'm representing the superscript of not. So if you are having an equation, a chemical reaction happening at standard temperature and pressure, your enthalpy can be at enthalpy not. Your Gibbs free energy can be Gibbs free energy at Gibbs free energy not, like as this superscript of 0 representing standard temperature and pressure. Okay, so keeping in mind that our equation for chemical equilibrium is our products over our reactants. Let's do an example problem. So we have okay. Sorry. So we have sulfur dioxide as a gas that's reacting with oxygen as a gas and forming sulfate or sulfur trioxide as a gas. So is this equation balanced?
Yes.
Oh,
No, this equation is not balanced. We have 4 oxygen and 3 oxygen. So our sulfurs are balanced, but our oxygens are not balanced. So in order to balance this reaction, what do we need to do?
Count them on both sides and make them equal.
Right. So hopefully all of you can do this pretty easily. You need a 2 in front of your sulfur dioxide here, and then a 2 in front of your sulfate over here. So now we have 2 sulfurs, we have 4, 6 oxygen, we have 6 oxygen. So check that it's balanced first, always. For the same logic, Abed, you could have put a half in front of this oxygen here because that's the exact same thing. If now I divide everything by 2, I'm going to have 1, 1/2, and 1. So it's the same balancing. All right, so we have this reaction, sulfur dioxide reacting with oxygen, forming sulfur trioxide, and we want to find KEQ. Oops, find KEQ. That's our goal, and at equilibrium and STP, we're given the following information. Sulfur dioxide, we have at a concentration of 0.9 molar. Oxygen, we have at a concentration of 0.35 molar. And sulfur trioxide, we have at 1.1 molar. So find KEQ. I'm gonna let you work on it for a couple minutes, just make sure you're able to do it a little bit.
Those values given, or did you compute those?
No, I gave those to you. Those are part of the problem statement. I would try again, Lula. Yeah. Dan, Zach, Dan, and Kat seem like they've got it. So I'm going to assume that other people are following suit. So this is really easy, right? KEQ is a representation of our equilibrium quotient. So the quotient of our products to our reactants. So using our KEQ equation, we have our products raised to their molar powers, their concentration raised to their molar powers, and then over the reactants, the same thing. So here our products are only this SO3. So we have our SO3, and then its balanced molar amount here is 2. And then we're going to be dividing by our reactants, which we have oxygen to the power of 1, and then sulfur dioxide to the power of 2. Now we have concentration information for all of these. So we have 1.1 molar squared divided by, what's an N? Divided by 0.35 molar to the 1 power, first power, and then 0.9 molar squared. So I'm going to have my calculator. I'm going to type this in, and then yeah, you get your KEQ value to be about 4.3 at STP, right? We're told this at STP. We are able to compute that our KEQ is about 4.3. So this is higher than 1, but it's lower than 1,000, and it's greater than 0.001. So we know that we have some products, some reactants. Since it's higher than 1, we have arguably more products than reactants, right, based on this quotient. But obviously, this is showing that it's really important to make sure you are balancing your equations correctly. So that should be totally, old hat to everybody here. I know chemistry is a prereq. Okay, one other thing to keep in mind, if I had given you a KEQ value and asked you to solve for the concentration of sulfur dioxide, you could work it that way as well. So it's not always going to be this, you're not always going to be given these same exact, every product and reactant concentration. Sometimes I could give you a KEQ value and ask you to solve for something else. Those get a little harder to type in your calculator and do the math. So just make sure that you know how to do that. All right. Okay, so let me check something in my book really quickly. All right, so I want to do another example. So this is an example of a combustion reaction. So combustion. So combustion is always when a fuel is oxidized and a large amount of energy is released. So a fuel such as octane, propane, butane, some sort of fuel is oxidized, so a reaction with oxygen, and energy is released. So combustion, we have combustion engines, we have combustion as a way of like producing energy. We've had this for quite a long time. So if we were to look at combusting octane, which has 8 carbons, so octane, C8H18, with I don't like the way that they set this up. Okay, I'm just gonna do it the way they did it. So this is example 15-1 in the book. I probably would have set this up a little bit differently, but for this product, you have some amount of octane that you are combusting with 12 kilomole of oxygen and a certain amount of nitrogen. So the way that they have this is they have, octane, some amount of octane plus 20 kilomoles of oxygen. This is a 20, this is a oxygen. 20 kilomoles of oxygen plus 3.76 additional moles of nitrate that are in that air. And this is reacting to a certain amount of carbon dioxide plus a certain amount of water plus a certain amount of O2 oxygen plus a certain amount of nitrogen. So try to spend the next few minutes balancing this equation. So setting up the problem, we know that we're combusting this octane fuel with some air that has oxygen and nitrogen in it. And we know that there's 20 kilomoles of this oxygen that's being provided. Some nitrogen is coming in. So just try to balance this equation.
Is that a 20 before the parentheses? Or is that, okay.
This is 20.
You said it's okay if we use fractions, right?
Yeah, you're gonna have to.
Okay. Bless you.
Thank you. Okay, it seems like some people have gotten the answers. So the answers are a 1. We already know this 20. Then we have an 8. Then we have a 9. Oops. A 9. Then we have a 7.5 or a 15/2. And then we have a 75.2. I'm not going to have much room here. 75.2. So did anybody not get those numbers and wants me to go through how I got those? And please don't feel like embarrassed. In fact, I'm just going to go through it quickly because I'm just going to, so everybody feels okay. Okay, so the way that I set up this problem is I look at all of the chemicals that are being represented, right? So here we have a carbon, we have hydrogen, we have oxygen, and we have nitrogen. Carbon, oxygen, hydrogen, oxygen, oxygen, nitrogen. Okay, so these are all the ones that are being represented. When I look at the information that I have, I can also maybe break this down a little bit easier for myself. The way that the book does it is they say, okay, we have information about these reactants. I'm trying to figure out information about my products. I'm going to label my carbon dioxide as an X, my water as a Y, my oxygen as a Z, and then my nitrogen as a W. So for carbon on my reactant side, I have 8 carbons. And on my product side, I have one carbon here. I have no other carbons. So therefore, it's equal to 1x. For my hydrogens, I have 18 on my reactant side. And my hydrogens on this side, I have 2 hydrogens here. I don't see them anywhere else. Okay, so this has to be equal to 2y. For my oxygens on my product side, I know I have O2 that is 20 kilomoles. So I have 20 times 2 on my reactant side. And on my product side, I have 2 as an X. I have 1 as a Y. I have 2 as a Z. And I have none as a W. And then for my nitrogen, I have 20 times 3.76 of my nitrogen. And on this side, I have, 20 times 3.76 times 2, right? Because I have 2 of these nitrogen. And then I have 2 of my W. So then I know that this X equals 8. That's the only consideration I have to make. So 8 is here. I know that Y equals 18 divided by 2, which is 9, which is my 9 here. I know that I have 2 times 8 plus 1 times Y plus 2Z has to equal to 40. So 16 plus, oh, I'm sorry, this should be 9. I should have typed in 9 because I know what Y is. 16 plus 9 subtracted from 40, 25. So 15 divided by 2. So Z equals 15 over 2, which is this 7.5. And now I know that I have, these 2's are going to cancel. So 20 times 3.76 is 75.2 is equal to W. So therefore, W is 75.2, which is my 75.2. Okay, any questions about balancing a combustion equation like this? The way that this problem was stated is we are combusting octane with 20 kilomoles of air. I'm sorry, we're combusting octane with air that contains 20 kilomoles of oxygen. And so you have to know that air only has 20% of the oxygen and like 78% of it is nitrogen, which is why if we're looking at something like air and you're trying to consider oxygen, you have to consider the fact that most of air is actually nitrogen. So I encourage you to look at example 15-1. I'm not going to go through that whole example right now. I just wanted to practice this balancing of equations. This example deals with an air-fuel ratio, which we're not really going to be going over. So as long as you can balance this equation, that's mostly what I wanted you to get out of this example problem. Okay, any questions? Great, chugging along. Okay, so something else that you should have seen in enthalpy and chemistry and maybe physics and other places too is this concept of enthalpy. And we've been looking a lot at enthalpy in chapters 3, 4, and 5. And we're going to keep looking at it now because this term of heat content, right, this enthalpy, it becomes really important for chemical reactions. So we should all know that enthalpy is a representation of the total heat content of a system. Total heat content of a system. Total heat content of a system, that's what enthalpy is. What equation relates enthalpy to internal energy? What equation relates enthalpy to internal energy? Yep. So enthalpy is equal to internal energy plus pressure times volume. So enthalpy is also dependent upon the direction of the chemical equilibrium. So dependent upon direction of chemical equation. So what are your products? What are your reactants? As a result, you need to balance and ensure the correct chemical equations. So balanced, correct chemical equations are very important. Balanced, correct chemical equations are necessary. Which, like, okay, duh, but it's just, this is where you'll lose points on the exam because it's not balanced, or it's not the right direction, or you left out something. So you have to spend time making sure that your chemical equation is balanced and correct. If we have a delta H that is our change in enthalpy of our chemical reaction, if this is negative, what is our term for this system? Like a delta H that's negative, we call what? No, I guess maybe I'm not phrasing this correctly. So when we have a delta H that's negative, we call this exothermic. So this is releasing heat. This is hot to the touch, it's releasing heat. Your change in energy of the system is, your change in your total heat content of your system is negative because you are releasing heat out of the system. So conversely, what's the opposite of exothermic? Endothermic, yep. So this is absorbing heat. This gets, it appears to get cooler to the touch. Does anybody know examples of chemical reactions or items you can buy at a store or things in your house that are either exothermic or endothermic? A stove. I'm not sure a stove is a great example of a chemical reaction that's exothermic because a lot of times it's just electrical. But I guess maybe, well, gas is just having a fire. Yeah, I'm not sure stove is a great example.
Would one be like liquid nitrogen or whatever they use to like make that, I don't know, like fried ice cream and stuff? Like, I don't know if you've heard of that. They have those restaurants. They're like dry ice. That's what I was thinking of. That's not the same thing. I don't know.
So dry ice and liquid nitrogen are just like super cooled substances. So they're not actually, yeah, I don't think those are great examples either. So I think Noah probably has the best example so far. If you have tinfoil and it works, toilet bowl cleaner, can you explain that? So you have like aluminum foil and you put toilet bowl cleaner on it and it gets hot? I haven't done that before.
You shred up tinfoil and you put it in a bottle and like you put the toilet bowl cleaner in it, you close the lid and it'll like explode like a dry ice bomb kind of, but it's like chemical.
Okay, yeah, so that's a good one, right then. So tinfoil plus toilet bowl cleaner. And then Emma had the other one that is the main one that I use as an example, toilet bowl cleaner, where the hand warmers, right? So if you've ever been to somewhere cold and maybe you went like skiing or you went on a snowmobile trip, they give you these little hand warmers and you crack it and then it starts to heat up. And that's because there's a chemical reaction that's going on inside of those that's exothermic. So those are both good examples, right? You mix these chemicals together, they react and they release heat. So your change in enthalpy from your chemicals that are reacting together is negative, they release heat. What about examples of endothermic reactions? Yeah, so a refrigerator system, ice cream, like maybe, yeah, like melting ice cube can be one. Yeah, I would probably say the refrigerant or like a coolant is a better example. The purpose of those is to chemically react and have a cooler temperature. Okay, and then one more thing about our change in enthalpy here. If we ever change in enthalpy and we denote it with this superscript of a 0, this is representing, remember, standard temperature and pressure. So our change in enthalpy at STP, that's our shorthand way of writing it. And then a lot of times you'll see this with a subscript of F, and this is talking about the enthalpy of formation. Okay. So I'm going to do another example, last one. So here's an example. We have our same system of our sulfur dioxide as a gas plus our oxygen as a gas is going to SO3 as a gas. This time I'm going to balance it the way Abed said, where I'm going to have the one have oxygen here. It's the same. The F sounds for enthalpy of formation. And so the problem statement says if 74.6 grams of sulfur dioxide, which has a molar mass of 64.07 grams per mole, is converted to SO3, what is the associated energy? What is the associated energy? Referring to heat energy. If 64.6 grams of SO2 with a molar molecular weight of, molar mass of 64.07 grams per mole is converted to SO3, what is the associated energy? Parentheses, heat energy. And we are told in this product that our change in enthalpy of this reaction is negative 99.1 kilojoules per mole. So this is an endothermic reaction. This is a negative value. And we know that for every 1 mole of SO2 that is reacted with oxygen, it releases minus 99.1 kilojoules per mole of energy, right? Like released. Or I guess you could say absorbed. In fact, let's just not name it something because that gets confusing. So that energy is released, but it's negative energy. So if you're releasing negative energy, you're actually absorbing that energy, which just gets confusing. All right, so we know that we have 74.6 grams of SO2. And then how are we going to get our associated energy? So take a couple, like 2 minutes, just try to answer this problem yourself, and then I'll answer it. Hint, it's very straightforward. Okay, yep. So we have 74.6 grams of SO2. We know that the molar mass is for every 1 mole of SO2. We have 64.07 grams. And then we know that for every 1 mole of SO2, we have to absorb 99.1 kilojoules. So our moles of SO2 will cancel, our grams will cancel. We're left with kilojoules, which is an energy term. So doing this math, yep, as everybody said, about a negative 115 kilojoules is this problem. Okay. All right, and then for the last thing for today, we have our enthalpy of reaction. Enthalpy of reaction. So the book has this as like an HR, which is fine. Sometimes they do H sub C if they're talking specifically about combustion, but for the enthalpy of reaction, this is the difference between the enthalpy of the products at a specified state and the enthalpy of the reactions at the same state for a complete reaction. The difference between the enthalpy of the products at a specified state, often like standard temperature and pressure, at a specified state, and the enthalpy of the reactants at the same state for a complete reaction. For a complete reaction. The difference between the enthalpy of the products at a specified state and the enthalpy of the reactants at the same state for a complete reaction. So enthalpy of reaction can also be our change in enthalpy, which is the enthalpy of our products. The summation of the enthalpy of our products minus the summation of the enthalpy of our reactants. And these enthalpy of the products and enthalpy of the reactants, these are the enthalpy of formations. So these are in a table, right? So for every, carbon dioxide, you're going to look up the enthalpy of formation. And then this whole equation here would be the enthalpy of your reaction. Okay. I think that is all I want to go over today. I think that's a good introduction to chemical thermodynamics. Please start reading chapter 15. I will warn you that I will be more heavily, the exam will more heavily focus on my class notes than the reading. The reading, I think, is very heavy on combustion systems and air ratios and theoretical air and things that I'm not really going to emphasize. So please, read over the chapter, maybe do a really heavy skim. But coming to the lectures, reviewing your lecture notes, that's going to be a lot more helpful in terms of doing well in the exam. Okay, so any questions that anybody would like to ask before I conclude class today? All right, then I will see you all on Wednesday on Zoom. Have a good rest of your day.
Have a good day.
Have a good one.
Excuse me.
Yes.
How long does it take you to upload the recording?
The recording of the lesson?
Yeah, I missed a few first minutes.
Oh, okay. So normally it has to process on my computer and then I upload it to YouTube. So it takes me about 2 hours, I think, but it should be up by this afternoon.
Okay, great. Thank you.
You're welcome.